As we move in to start studying the dynamics of nonlinear systems, it's important, one of the distinguishing characteristics is the fact that nonlinear differential equations don't necessarily have only one equilibria. So it's possible for them to have multiple equilibria, which remember says that the derivative is equal to 0. So if the system state is representing something like position, velocity, acceleration, then that means that that is a place where all of those things are not changing. So the time derivative is equal to 0. And so that's true for other systems where you're modeling human intent. This is where the state is no longer changing. And so that those are important points because those are either where the system converges to or diverges away from. And so an important result is the fact that if you zoom in really close to an equilibrium value, any of these equilibria values in a nonlinear system around that local neighborhood is isomorphic to a linear system, which means that we can think about those as linear systems if we zoom in close enough to that. And so the whole idea about analyzing nonlinear dynamical systems from this linear perspective is to get an overall picture, usually a qualitative picture, of what the dynamics look like of this system by stitching together the local behavior that's given by each equilibrium, and that local behavior is determined based on the linear system that mimics that nonlinear system around the equilibrium. And so remember, it's important, so when we talk about linearization, it's important to remember that we are linearizing around a point x0, and typically that is going to be an equilibrium of the system. At least for the point of this course, that's what we'll do. And so linearization means let's write the nonlinear system as a linear system. And so the way we do that is we define this perturbation, the state perturbation delta x, which is simply just a small amount away from that this point x0. So this x0 is kind of the center, and we're taking a look at the neighborhood around that center, and we're saying that we can rewrite the dynamics of that perturbation. So it's how the perturbation changes in time with respect to a matrix A times that perturbation. And that A is the important part. That A is going to be the Jacobian of the function f, our original dynamics function, vector field, evaluated at the point x0. And so using that matrix, we can then evaluate this equilibrium x0 as a node, a focus, a saddle, etc. And so what we're going to do next is define what that Jacobian actually is. As we start to talk about the Jacobian, it's possible to think about it as the generalization of the tangent line. So the tangent line was for a function that had as an argument a single number and output a single number. So the function f that we have is a vector valued and also takes in as an argument a vector. So the state takes in as a vector, so f depends on x. X is a vector of length n, and this outputs x dot, which is also a vector of length n. And so it's important then, since f is a vector, it has functions f1, f2, all the way down to fn. Each of these is going to be a function of x1 through xn. We need to take all of those derivatives, and the Jacobian is our way of organizing that. And so we just have all of the combination of derivatives that are possible from df1, dx1 down to dfn, dxn. And so the important part here is that these functions depend on all of these variables, and so these are partial derivatives. So let's see an example of how we could linearize a nonlinear dynamical system. So in this case, we are going to write the first step is to write our differential equation in terms of a state, x1 and x2. And so the first step is to write that x1 is just going to be theta, and so that makes x2 is equal to theta dot. This then tells us x1 dot is theta dot, theta dot, and that is in fact x2. x2 dot is then theta double dot, and this is where we get to use our differential equation here, which says that theta double dot is equal to minus g over L sine of theta. And sine of theta, we can write that into our new states as sine of x1. And so that's exactly how we get this vector expression, and that defines what f actually is. So f1 is just this function, f2 is this function. And so our first step is to identify where the equilibria are. And so that's where x dot is equal to 0. So we set this f equal to 0. And that happens when x2 is equal to 0. And essentially sine of x1 is equal to 0. And so sine of x1 is going to be 0 anytime x1 is going to be a multiple of pi, an integer multiple of pi. So at 0, at pi, at 2 pi, at 3 pi, and so on. And so what we're going to be interested in then is what does the Jacobian look like? What does that linear behavior look like at each of those equilibria? So if we take the Jacobian of this general function, then what we do is we take the derivative of x2 with respect to x1, that's 0. The derivative of x2 with respect to x2, that's 1. Derivative of minus g over L sine x1 with respect to x1, so that it does depend on x1. So what's the derivative of sine? It's cosine. So we just keep this coefficient and we get the cosine of x1. The derivative of the second term of f with respect to x2 is just 0 because it doesn't depend on x2. And so this then is the Jacobian that describes in general what the linear behavior would look like around any point. And now what we want to do is find it around the point where the first element is some multiple of pi and the second element is 0. So x2 is going to be 0 and x1 is going to be some n pi. So if that's true, then the only thing, x2 doesn't appear here, but here's x1. And so what we're going to do is we're going to plug in n times pi here. And so depending on whether that's n is 1 or 2 or 3, that's going to change. So if it is cosine of pi, that's going to be a minus sign, minus 1. If it's 2 pi, then that means it's going to be positive 1. So that means that in the case where it's even, so at 0, at 2 pi, we're going to keep this minus sign because the cosine will just give us a positive 1. So that minus sign stays. When it's odd, then we get a minus sign, extra minus sign that cancels this out. And so we get a positive sign here. So depending on which equilibria we're talking about, we get different linearizations. And if we find the eigenvalues, which I recommend that you do, go ahead and go through that process, you'll see that in fact it's easy to calculate them, and it's just they're complex values in this case, and you're getting, so in the even case you're getting complex values with 0 real part, which is that center case that we talked about, which we said does give us some problems when we're analyzing stability. When it's the odd equilibrium, then we actually get plus or minus a real value, which gives us a saddle. So when we compose this phase portrait, this means that the equilibria here, the even equilibria, looks like a center, and the odd equilibria, so this is at pi, and this is at minus pi, and this is at 0, that the overall phase portrait looks something like this, where locally around this equilibria it looks like a saddle, locally around this equilibria it looks like a center, and around this one again looks like a saddle. And so this repeats both to the left and to the right. If we add damping to our pendulum, so in this case we have this damping term here, then I recommend that you pause the video, take a look, form the state space equations, and then make sure that you get these two Jacobian matrices, depending on whether you have n pi being even or odd. And so in this case, if you again, I recommend that you find the eigenvalues, you'll see that this has complex values with negative real part. And so that means that you have a stable focus. In the case of the odd, you still remain this having this saddle. And so now what was once originally a center at the origin, around the origin, and around every even multiple of pi, now is actually a stable focus. And so here, locally around here, you still have saddle points. Around here now, you have a stable focus. And so simply by adding damping, you can see now that that this changes this equilibrium. And I urge you to think about what this phase portrait is actually telling you now in the context of x1 and x2 representing theta. Remember, x1 is theta and x2 is theta dot. And so what is it telling you about the motion of this pendulum? And so now as we understand how to linearize certain equilibrium around that equilibrium to get local behavior, then what we have to do is we have to start stitching these together to get global behavior. But one of the challenges is how exactly this gets stitched together. And so I'm just presenting you with a simple example where if you had a saddle point and a spiral focus or a stable focus, that you could combine those together, for example, like either of these two ways. So here, the spiral focus spirals into x2, so locally around here, it looks like that stable focus. Locally around here, it looks like the saddle point. But the question is whether these eigenvector directions correspond to somehow line up so that we actually create this orbit that happens around the stable focus. The other alternative is that they don't line up and that along here somehow we get trajectories that then spiral in, and so other trajectories out here would also move along here and they would also spiral in, and somehow there would be this breakpoint at this level. So there's some ambiguity, and so it's important to be able to stitch these together and understand where the ambiguities might happen. And so one thing that I'll let you think through and we can talk about in class is understanding why we don't allow solution lines to cross. How we know that, for example, the spiral focus doesn't look something like this, where it actually crosses the streamline right there.